Okay folks, so today's video is on electrolysis, and electrolysis is a fancy name for breaking stuff down using electricity. But hopefully by the end of this video you're going to be experts and know exactly what this means anyway. Right, so we're going to start off, as always, with a quick quiz. So would like you to genuinely pause the video and have a go at these questions. So I'm going to give you 5 seconds before I go through them. 5, 3, 2, 1. Okay, so let's go through these questions. Make sure you genuinely attempted them right though, yeah? So what does the state symbol AQ mean? So it means aqueous, which means dissolved in water. What is a cation? So all of these questions are actually going to be useful for today's lesson, and you should know all of the answers to them from earlier on in the course. So what is a cation? A cation is a ion with a positive charge, is a positive ion. What is an anion? So an anion is a negative ion. When do ionic substances conduct electricity? So they can't conduct when they're solid, but they do conduct when they are molten or aqueous. And what's the charge of an electron? Electrons are negative. They have a charge of -1. So that's that one. Right, so on to electrolysis for today. So electrolysis. So that's the definition that you need to make yourself aware of. Electrolysis is the process of decomposing an electrolyte with DC electricity. So decomposing an electrolyte with DC electricity. That doesn't necessarily make a lot of sense to you at the moment, so I'm going to break down a few of the words here. So decomposing, that's a fancy word that means breaking down. Breaking down. So you're taking the compound and you're splitting it apart. So decomposing something, breaking it down. An electrolyte, so that's the first part of the lesson we're going to learn about. So an electrolyte is an ionic compound in the molten or aqueous state. So molten just means you've heated it up until it's melted, right? It's a liquid, put brackets with a little L, and aqueous is dissolved in water, so brackets, AQ. And if you remember from the quiz, if you've got an ionic compound that's molten or aqueous, it can conduct electricity. So that's the electrolyte. So you get your ionic compound, you either heat it up incredibly hot because they've got a high melting point, so it's like molten, or you dissolve it in water, so it's aqueous, and then that is your electrolyte. And then DC electricity, DC, and you will eventually study this in physics. This stands for direct current. And direct current is a current that always travels in the same direction. So if I draw a little circuit here, so that's the battery, let's connect it up to itself, and so you'd have the current is always flowing the same way around that battery. The opposite of DC is AC, and that stands for alternating current, and that constantly changes direction. So the electricity that comes out of your plug sockets at home is an alternating current, and that changes direction 55 times every second. It's got a frequency of 55 hertz, which means 55 times a second electricity goes that way, then that way, then that way, then that way, and it changes direction 55 times. So we don't want to use alternating current for this. We have to use direct current, and direct current flows in one direction, doesn't change directions. Okay? Right, so if we go back to this, electrolysis is a process of decomposing an electrolyte with DC electricity. So it's breaking down a molten ionic compound or an aqueous ionic compound, and we're using a direct current to do it. Right, Again, that's probably not enlightened you that much, but when we come back to this in sort of 5 or 10 minutes time, it should hopefully make a lot more sense to you. So let's draw a basic setup for electrolysis. So we're going to need our DC supply. So that's our direct current supply. We've got a couple of wires coming from it, and then we need something called an electrode. We tend to use, you can use lots of different things, but the most common one is graphite. So graphite conducts electricity and it's not particularly reactive. And then we'll put this in our container, and then we're going to add our electrolyte here. Right, so I'm going to add some labels to this. So these are called, I'll do the labels in a different colour. So that's an electrode and that is an electrode. Now one of these electrodes is going to be positive and one of them is going to be negative. Let's just do this one here. So if I said, I'm going to call this one, actually, I'm just going to write positive electrode at the moment. So positive electrode, which means over here, this one is going to be the negative electrode. So we've got the positive electrode and negative electrode. I'm just going to erase that label just before my diagram gets too confusing. So they're both electrodes. This one's a positive one, that one's a negative one. And then this liquid, so this isn't a complete circuit at the moment. If I erase this, so we've just got these two electrodes here, and it's not a complete circuit. Apologies if you can hear some noise in the background. There's a construction site right outside the door, like 5 feet away from me. Right, so this isn't a complete circuit at the moment, so electricity can't flow around. So we need to connect them up. So we add our electrolyte, and this is why it's important that it's an ionic compound, and it's got to be either molten or aqueous because it needs to conduct electricity. So this is our electrolyte. So now we've got a complete circuit. And the example electrolyte that we'll use, we will use lead bromide. So lead bromide is, lead is Pb, bromine is Br, it's PbBr3 because it's made up of Pb3+, so that's an ion of lead which is got a positive charge of +3, and it's made of Br-, remember that is technically -1, but scientists are really lazy so we don't write the 1, so we just write it as a minus, and then we need to balance those charges, so there's 3 of them, which means we've got 1 ion that's Pb3+, and 3 ions that are Br-. So our electrolyte is lead bromide, which means in this we have got lots of Pb3+ ions in here, and we've also got some Br- ions in there. And if you remember back to the quick quiz, right, what is a cation? A cation is a positive ion. So that is a cation because it's a positive ion. And cations get attracted, it's positive, it goes to the negative electrode. So this electrode has a name, it is called the cathode. So positive cations go to the negative cathode. What do we call negative ions? Back to the quick quiz. Negative ions are called anions. So the negative anion goes to the positive electrode, which is called the anode. I'll just write that so it's a bit clearer. Anode. You might be able to hear my children in the background as well. The joys of home working. Right, so negative anion is attracted to the positive anode. the positive cation is attracted to the negative cathode. So when we turn this electricity on, all of the positive ions in this solution go straight to the cathode, and all of the negative ions in this solution go straight to the anode. So without the electricity, they're all just floating around in there, positive lead ions, negative bromide ions, floating around as molten lead bromide. So it's molten, so it needs brackets L. So molten lead bromide, that is our electrolyte. If you remember back, what's an electrolyte? It's an ionic compound in the molten or aqueous state. So the one we're talking about is molten. So we've got lead bromide, it's molten, all the ions floating around. As soon as we turn the electricity on, all the positive ions, the lead, go to the cathode, the negative electrode, and all the negative ions, the anions, go to the anode, the positive electrode. And that's where we're gonna, the next part of the video is gonna break down what's actually happening there. Right. So let me just roll out the quiz. Okay, so there's couple of new terms to talk about here. Just put that in there so you can see it. So I'm going to talk about first what is going to happen at the cathode. And if you remember, the cathode is the negative electrode, and it is where cat ions go. And cat ions are positive ions. So we've got our lead, Pb3 plus ion. It's come across to the cathode, and what happens to it? It gains electrons. So we're turning this back into lead. The whole point of electrolysis, so we were breaking stuff down using electricity. So we're taking our lead bromide and we're going to turn it back into lead and bromine. So we've got our Pb3 plus. If we want to turn it back into lead, well, lead is just Pb. So how can we turn Pb3 plus into lead? Well, we need to give it 3 electrons because it needs to gain. So an electron is E minus, but this has got 3 pluses, so it's going to need 3 of them. So it goes Pb3 plus 3 electrons turns back into Pb. Okay. What is happening at the anode? So the anode is the positive electrode, and it is anions that go to the anode. So anions are negative ions. So negative ions go to the positive electrode. So anions go to the anode. Cations, which are positive, cations go to the cathode. Right, so our negative ions here, the negative ions are Br minus. So we have Br minus, and that needs to turn into bromine, which is Br. If you've got a periodic table to look at, bromine is in group 7. So it's a non-metal, it's in group 7, it's not got enough electrons. So whereas metals we just write as like Pb, or if it was iron we write it as Fe, or copper we write it as Cu. They don't have a little number after them. For non-metals, so for those in groups 5, 6 or 7, bromine goes around in pairs. It goes around as Br2. Okay, so let's work out way of balancing this first. So Br2, that means we're going to need 2 bromines. So we're going to need to put a big 2 over here. So we've got 2 lots of Br minus, will turn into Br2. So we've balanced the bromines, but we need to balance the charges. If you look at this one, we've got 3 positives, and then we've got 3 negatives. 3 positives, 3 negatives cancel out. Over here we've got 2 negatives, but over this side we've got no negatives, so we need to make sure they cancel out. The only thing we can do is add electrons. So if I add electrons to this side, I'm going to be adding more minuses, which doesn't help me out. I need to add electrons to this side, so I need to add 2 electrons here. So what this is showing is the 2 bromide ions have both lost an electron. So the electrons here are on the bromines, and here they've been ripped apart from them. Okay? Stick with it if you're a little bit lost, because there's a couple of bits which will hopefully just pull all of this together now. So I'm running out of little boards to write on now. I don't want to rub any out yet because I'm going to be coming back to them. Right. Oil rig. This is an acronym. This isn't actually got anything to do with oil rigs. So oil rig, what this stands for is oxidation is loss, and then we're talking about electrons, right? It's loss of electrons, and reduction is gain of electrons. So, and I've probably picked the dirtiest whiteboard to write this on, so apologies if you can't read it properly. So we've got oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So if we go back to this, and if you remember, so I'll just write it up here, oil rig. What is actually happening here? Well, the lead ions, that's gained electrons. So this is reduction. So this is an example of reduction. The lead ion is gaining electrons, turning back to a lead atom. What's happening here? Well, the bromide ion has lost electrons. So this is an example of oxidation. So in an oxidation reaction, something's losing electrons, and in a reduction reaction, something's gaining electrons. But the reality is, if you're gaining electrons, you've got to get them from somewhere, and we're getting them from here because this is losing electrons. So when these two processes happen, we actually call it a redox reaction. And a redox reaction is when something is being reduced and something else is being oxidized. So something is reduced, reduction is gain, something's gaining electrons, and something's being oxidized, something else is losing them. So this is a redox reaction. And I'm going to just come back here, and hopefully this is the bit that's going to tie it all together. So when we come back and look at this here, what actually happens at the anode? So we talked about this, if I pull this back in, so the bromine ions, they're losing an electron. So this electron here gets ripped off, and it goes into the anode. And then that electron gets pumped around the circuit by the battery. And so the electron comes down here. And then that electron, what's happening at the cathode? Well, we looked up here, this is gaining electrons. So that electron goes and joins onto PB. So when this happens here, so we'll have another Br minus, and that electron gets ripped off, goes onto there because this has been oxidized, it's losing the electron, and the electron gets pumped around and then goes onto the lead. So at the anode, all of the negative ions are drawn towards this electrode, remember it's positive, and then they all lose their extra electrons, the electrons get pumped around the circuit, and over here the electrons get given to the positive cation here. So we're losing a whole bunch of electrons here, and then we're gaining a whole bunch of electrons here. Yeah, I will, do you know what, I'll rub this one out. I might regret this because I might have to end up drawing it again in a minute. So in terms of little tricks to help you remember things, so you've got oil rig for oxidation is loss of electrons and reduction is gain of electrons, and then you've got oxidation, because oxidation happens at the anode. And then you've got reduction, because that is not, I've put two C's in it. Right. We'll just pretend that didn't happen. Reduction, because reduction happens at the cathode. So oxidation is loss of electrons, reduction is gaining electrons, and oxidation happens at the anode and reduction happens at the cathode. So going back to what is electrolysis. So electrolysis is the process of decomposing an electrolyte with DC electricity. So breaking down an ionic compound using electricity. Okay, and going back to this, why does it have to be DC? So if let's just show this here, just draw this quickly. Let's stick our electrode here, stick our other electrode there. Right, if we used AC electricity, so we use DC, so it means if we make this one negative, so and we make this electrode positive, and if you can just very quickly try and remember the names of these. So this electrode is negative, which means it's called the cathode. This electrode is positive, which means it's called the anode. And this positive ion is going to go that way, and the negative ion's going that way, because it's a DC supply, that stays the same. If we used an alternating current, an AC supply, well, the direction of current would change like 55 times every second, which means this electrode would be going positive, negative, positive, negative, positive, negative. And this one would be doing the same. It would be turning from negative to positive to negative to positive. So all these ions in the middle, this positive ion would be like, I want to go here, no, I want to go here, no, I want to go here, no, I want to go here. And it would just be like vibrating in the middle between them, and this would be doing the same thing. So a alternating current absolutely does not work for electrolysis. So you've got oil rig. For oxidation is loss of electrons, reduction is gain. You've got oxidation happens at the anode and reduction happens at the cathode. So we're going to go through one more example here, and then hopefully this will clear up a lot of questions. So we're going to use a different one. We're going to talk about electrolysis of molten copper chloride. So if I tell you copper chloride is CuCl2, now if that's going to be our electrolyte, it means it needs to be molten, so we need to heat it up so it's a liquid. And the ions involved, copper, we're going to say Cu2+, and then we've got chlorine, which is Cl-. So we've got two of them. So I want you to talk, I'm going to explain this one and then I'll get to have a go at another one. So if we have the cathode, right, so what's going to go to the cathode? Well, cathode is negative, which means we attract cations, which are positive. So the positive ion here is the Cu2+, so we get Cu2+. And what happens at the cathode, so if we go back, at the cathode we get reduction. So we're going to have reduction, and what is reduction? Reduction is gain of electrons. So this is going to need to gain electrons. How many electrons is it going to gain? Well, it needs to gain 2, because it's got 2 positives, so it needs to gain 2 negatives. And then that means we're going to make copper, which is going to appear as a solid. Right. Although actually it's molten, so it would be molten still. Right. So we're going to have, that is what's happening at the cathode. What happens at the anode? I'm not sure, but this is on the screen. Let me just shift it up. Right, what happens at the anode? Well, the anode is positive, which means it attracts anions. Okay, so really annoyingly, and the video stopped recording, and I didn't realise and carried on speaking for like another 10 minutes. So I've just gone back and checked how far it got. So at the anode, it attracts anions, and if you remember, oxidation happens at the anode. Oxidation happens at the anode, and oxidation is loss of electrons. So we've got Cl minus, and it's going to lose electrons, so it turns into Cl and an electron. This is a non-metal. If you go back and look at the covalent bonding topics, non-metal, it's in group 7. It goes around in pairs. So if we've got 2 chlorines, it means we need 2 of those, which means we've got 2 minuses, which means we need to lose 2 electrons. Right. These two are called half equations because this is what's happening at the cathode, this is what's happening at the anode. They both represent half of the process. So 2 half equations make a whole equation. So just to explain that very quickly, if I'm going to join these together, it means I join together the left-hand side and then the right-hand side. So I'm going to end up with Cu2 plus 2E minus, that's that, plus this one, plus 2 lots of Cl minus, and then I'll do the right-hand side. That's what I get, Cu plus, in the right-hand side of these, Cl2 plus 2E minus. So I've got those left-hand sides there, these right-hand sides there. And then I can cancel bits. If you look, I've got 2 electrons on this side, and I've got 2 electrons on that side. So I can cancel those out. And so what I actually end up with is Cu2 plus 2 Cl minus goes to Cu plus Cl2. And this is actually what's happening. So we've got copper ions and we've got chloride ions, and we're turning them into copper and chlorine. So we had sort of copper chloride, and then we've turned it into copper and chlorine. So if you look at these two, this is why it has to be molten or aqueous, right? Because if it was solid, it would just be CuCl2. But when you melt it, it means the ion, or dissolve it, it means the ions are all floating around separately. So this CuCl2, instead of being sort of a Cu2 plus joined onto Cl minus, yeah, instead of being like that, when we melt it, it means they're all floating separately. So we've got copper chloride made of these two, and when we do electrolysis on it, it splits into those two. So it's quite a lot to remember from today. You've got to remember the anode and cathode and the charges. You've got to remember cations and anions you should have remembered before. You need to know, so what is electrolysis? It is decomposition of an electrolyte using direct current. So you need to remember what is decomposition, what's an electrolyte, and what is direct current. And then you've got these examples. You should be able to do these for any molten ionic compound, because all that happens is you work out what the cations are and they go to the cathode, and at the cathode it's reduction, which is oil rig, so it's gaining electrons, and at the anions go to the anode, which is oxidation, which is oil rig. So this is kind of the key to the whole thing. It's a good point to stop the video because the construction work has just started up outside again.